Okay. Okay, so last time I talked about suffix arrays, and I also introduced at that point something called, at the end of that lecture, something called the LCP array. And that's principally what I want to talk about today is the LCP array, what you do with it, what it is, what you do with it, and how you build it in linear time. So I'm going to start again by putting up the same suffix tree. Both of these concepts are related very strongly to a suffix tree. And I'm going to put up the same string I had last time, A, B, D, A, B, C, A, $, and the same suffix tree that I had last time. This was for suffix 6, and then we had A, D, A, B, C, A, $. This is for 1, position 1. Over here was C, A, $. That was for suffix 4. And then here was just a $, suffix 7. Then we had a B, C, A, $. That was 5. D, A, B, C, A, $2. And just one more. This one was D, A, B, C, A, $3. Okay, so this is a suffix tree for this string S. And one of the things I said last time about the suffix array is that you can get it by doing a lexicographic depth-first traversal of the suffix tree. So that would, since $sign always is lexicographically smaller than any other character, we would go down here, we get a 7, and then come up here, down there is a 4, then a 1, go back up, next is a 6, B, C was a 5, 2, back up here, and then a 3. Hopefully that's right. Let me look at this. 7, 4, 1, whoops. Where did I go wrong? After 1, we're supposed to go to 5. Yes, of course, because B is smaller than C, so that should have been a 5. And then 2, 6, 3. All right. 2, 6, 3. All right. So actually, let me rewrite that. 7, 4, 1, 5, 2, 6, 3. And that's the suffix array for this sequence. Now, what I want to do is take a look at every consecutive pair of entries in the suffix array and ask, what is the depth? What's the string depth? Or how many characters do they have in common between the suffix starting, let's say, at position 4 and the suffix starting at position 1. So we're going to do that for every consecutive pair here. So the first one we're going to ask about is what's the longest common prefix between the suffix that starts at position 7 and the suffix that starts at position 4. So we can find the suffix at 7 and the suffix at 4. And the point is that 7 and 4, why do I have a 1 there? Oh, yeah, here's 7. No, I'm sorry, something went wrong here. This is not written right. That's right. Okay, sorry. So this is the suffix tree. I had that done incorrectly. This is the suffix tree for this string. And so the point is that the suffix beginning at position 4, 1, 2, 3, 4, 5, 6, 7, the suffix that begins at 4 and the suffix that begins at 7, they agree for one character, namely the character A. And so I'm going to put a 1 here, which says that, again, it says that the suffix beginning at 7 and the suffix beginning at 4 agree for one character. And also note that if you were to walk up from the leaf labeled with 7 and the leaf labeled with 4 until you reached a node that they had in common, an ancestor that they have in common, the depth of that ancestor, the number of characters written on the path down to that ancestor, that common ancestor, is exactly the number of characters that they share, the number of characters they share in their prefix. So the length of the longest common prefix of two suffixes is equal to the number of characters written on the path down to their lowest common ancestor. I'm going to write that up over here, and then we'll come back and continue the example. The length of the longest common prefix, the longest prefix that they have in common, that they agree on, the length of the longest common prefix of two suffixes of S, let's say suffix I, that's the one that starts at position I, and suffix J, that's the suffix that begins at J. The length of the longest common prefix of those two suffixes is equal to the number of characters on the path in the suffix tree for S, on that path to the lowest common ancestor node of the leaf labeled with I and the leaf labeled with J. Okay, so this is saying explicitly what I was saying in words when we looked at the tree. And now let's go back to the tree and see some more of these. Okay? Let's look at 4, 1, those consecutive pairs of that consecutive pair. So this represents suffix 4, which is right here, that's leaf, and this represents suffix 1, which is right here. Okay? And I drew the tree wrong again. Somebody should have stopped me. You saw it last time. Okay, a redraw of the tree. There's supposed to be a B in here, and then this one goes off as CA $sign to 4. Okay, so that's the proper, that's what should be in the suffix tree there. Okay, so getting back to the question of what's the longest prefix that's common to suffix starting at 4 and the suffix starting at 1. We could look up here. Starting at 4 is here, and starting at 1 is there. So that's A, B. That has length 2. And also, if you walk up from the leaf labeled 1 and the leaf labeled 4, you find the common ancestor, the lowest common ancestor, the node that's a common ancestor of both of these, and it's the lowest one in the tree, that's the common ancestor. And it has, the number of characters on its path is 1, 2. Okay? So let's do 1, 5. You have 1, 5. You walk up to, there's a common ancestor that's there, which means it's 0 is what's common to the prefix at 1 and 5, and you can verify that by looking here. The prefix starting at 1 is A, the prefix starting at 5 is B, so that's a 0 commonality. Then 5, 2 is 1. 5, 2, you go up there and there's a 1, and 2, 6 is a 0, and 6, 3 is a 0. Okay, so this vector here is the string depth. The number of characters that are written along a path is called the string depth of that path. So the numbers here are the string depths of the path down to the node that is the lowest common ancestor of a consecutive pair of elements in the suffix array. So this is the suffix array, and this array is called the LCP array. The suffix array for S and the LCP array for S. And I'm going to define this in another way. I defined it differently last time as well, but I wanted to give you this visual picture of what the LCP array is. Okay? So the length of the longest common prefix is equal to the number of characters, and that is defined as LCP of, this definition is more general. LCP is just going to be lengths for two specific ones. Okay, so let's get to the definition of LCP, or more formal definition of LCP. So actually, to get that, we want to define SI. Here I said it SUFFI, but let's just simplify it. SI is going to denote the suffix of S starting at I at position I. Okay? And then another definition, the predecessor of I is equal to the value in the suffix array for S written just before the position where I is written. Okay? So this is actually what I wrote last time in the last lecture, and let's just rewrite over here. Well, let's go back here, and on this whole example, let's just use this example here to look at the predecessor values. So here's the suffix array for S. We have the suffix array. And so we can look at the entries here, and we can use this by the definition to find out what the predecessor value is. So the predecessor for 7 is empty because there's nothing that precedes 7 in the suffix array. But the predecessor for 4 is equal to 7. And the predecessor of 1 is equal to 4, and so on. Let's just write one more. Predecessor, for example, of 6 is 2. Okay? So there's some notational load in this lecture, but anyway, this is the definition of predecessors. The key point here is that when we talk about the predecessor of 4, for example, we're not talking about the position 4 in the suffix array. We're talking about where 4 is, where the value 4 is in the suffix array, and then we look at the element just to its left. Okay. Now I want to relate this, though, to to the way the suffix array was created. Not the linear time algorithm that we did last time, but the creation of the suffix array that you could do from a suffix tree. This is conceptual. This is for conceptual purposes. Algorithmically, we build a suffix array with the interesting and elegant algorithm that we did last time. But conceptually, to understand things, it's very useful to think in terms of the explicit suffix tree. So the suffix array, remember, was could be found by a lexicographic depth-first traversal of the suffix tree. So it goes down to 7 first, and then it goes to 4, and so on. And the point is that if you think about it that way, if you think that you're building up the suffix array by doing a lexicographic depth-first traversal, then really all that the predecessor is just the leaf that's encountered just before the leaf you're focusing on is encountered. So there's, say, the predecessor of 5, if we're thinking about the depth-first traversal, the predecessor of 5 is just the leaf that's encountered just before the leaf for 5 is encountered. Okay? So it's going to be useful to keep the tree image in mind, even though we have this purely notational definitions as well. It's just much, much harder for me to keep the notational definitions in mind, and much easier to think about what's going on in the tree. So the predecessor of I is simply what label is on the leaf that's reached in this lexicographic depth-first traversal just before the leaf for I is reached. And the predecessor values, well, we've written down some here. Let me write up the entire ones. Well, we have them. I mean, okay, you can see the predecessors from there. And then, if you think about it that way, what is the LCP value? It's just, what is the, if you're going to go, we know we visit leaf 1 before we visit leaf 5, just before leaf 5. So from leaf 1, in order to get over to leaf 5, we have to go back up the tree. We're doing a lexicographic depth-first traversal. We have to go back up to some node before we come down to leaf 5. From leaf 1, we're backing up to some node and going back down to leaf 5. And the LCP value is just exactly the string depth of the node, the highest node that you reach when you go between those two leaves. You're going up for a ways, you hit a node, then you're going down for a ways. And what is the string depth of that node where you change from going up to going down? That is exactly the LCP value. Okay, so I have several different ways of trying to motivate what the LCP value is. I haven't shown you at all why it's useful, but hopefully between all these different ways, the formal definition and the sort of more graphical view here, you can hold it in your head. Let's just do one more example let's look at the LCP value of 1 and 4, okay, and in terms of this last interpretation, we were saying, well, we know the depth-first search, the lexicographic depth-first search, hits leaf 4 just before it reaches leaf 1, and in order to go from 4 to 1, the depth-first traversal had to go up a ways, in this case just a single edge, but in general it could be more, up a ways and then down a ways, and then the string depth of the node where you change from up to down is exactly the LCP value here at 1. Okay, so let me define finally a formal definition of LCP. Okay, LCP of suffix K and suffix that's the predecessor of k, and this is exactly what we've been talking about. This is the suffix that begins at k, and this is the suffix that begins at the predecessor of k, okay, is equal to the string depth of the common prefix of sk and s predecessor of k. Ooh, I hope you can read that in the. I hope you can read that on the video. Maybe you can just look at that closely for a minute. So the LCP of the suffix that begins at position k and the suffix which begins at position identified by the predecessor of k in the suffix array is equal to the string depth of the common prefix of sk and s predecessor of k in the suffix tree. Okay? In the suffix tree for s. So that's what LCP of that is equal to. Okay. Now, our problem, our general problem is going to be how do we compute the LCP array quickly? And that had been an open question for some time, whether you could compute the LCP array in linear time. And I'm going to show you how to do that in linear time. The algorithm is actually quite elegant and simple after it was digested for a long time. It was originally written in a paper that was very hard to read, partly because it had typos in it. And I think it had typos in it partly because it was done purely notationally. But once you start thinking about it in terms of the actual underlying suffix tree, then you can see what the idea is. And then you can go back and correct the typos in the purely notational exposition. But before I get into how you build the LCP array, you might want to know what it's good for. And the answer is that the suffix array, along with the LCP array, pretty much allows you to do in linear time all of the interesting problems that had been string-type problems that were solvable, that are solvable in linear time using a suffix tree. So one of the reasons that suffix trees became very powerful and interesting is that there's a whole host of string problems that can be solved in linear time after you've built a suffix tree, which we know we can also build in linear time by Yukonen's algorithm and so on. And since the suffix array is more space efficient and has other efficiencies, it was of interest whether you could solve all those various problems in linear time just using a suffix array. Well, the answer is you can't. But along with a suffix, with the LCP array, people have shown a few problems at a time that all the known interesting problems on suffix trees can be solved in linear time on suffix arrays. There's no meta theorem. There's no theorem that says that any problem that can be solved in linear time with a suffix tree can be solved in linear time with a suffix array and a LCP array without using more space. I say that because one thing I'm going to show you is that, in fact, from the LCP array and the suffix array, you can build the suffix tree. Okay, so that's the first thing that I'll show you that suggests the utility of the LCP array, is that with the suffix array and with the LCP array, those define the suffix tree, and you can build that suffix tree in linear time. So let me write that up. Claim with the suffix array for S and the LCP array for S, one can build the suffix tree for S in linear time. It means order n time where the length of S is equal to n. I'm not sure I told you what LCP stands for. That stands for longest common prefix. Okay. All right. So here we have the suffix array, and here we have LCP. Okay. Let me just stand back. So no, I think I have it on my notes. I wanted to write down the. I'll just stand back so I can see it. 7415263. 7415263. 1, 2, 3, 4, 5, 6, 7. Good thing it's only 7 because I took a course on memory once where they say that 7 is about the longest number of digits that you can hold in your head at once. After that, it's without training, it becomes very difficult. All right, and then the suffix, the LCP is 120100. 120100. Okay? Stop me if I did anything wrong. 120100. Yeah. Okay. I claim that from these two arrays, you can build the suffix tree for S. And in linear time. Now, one thing I have to add, when I wrote up the suffix tree, I drew up the suffix tree earlier today, and in last lecture, I explicitly put the characters along the edges that label the edges. And as we know from our earlier discussions of suffix trees, when you build a suffix tree in linear time, there isn't time to explicitly write down the characters that label an edge. But because the characters that label an edge actually are a substring, on any edge, the characters that label the edge form a substring in S, we can represent that substring just by the starting position and the ending position of that substring. So we'll be doing that here as well. So initially, we're going to, in order to build the suffix tree, we're going to start from the left end of the suffix array, and we're going to go left to right through it, and we're also going to be going left to right through the LCP. So we start out with 7. So we know that there's of course, oh boy. In the suffix tree, there's a path to the leaf labeled 7. And I'm going to represent it that way, and represent that the characters that label this path are just the substring that starts at position 1 and goes through position 7. No, that's not right. Yes, it is. No, it's not right. Excuse me. This go from 7 to 8, which is just the dollar sign. This is where the dollar sign was at position 8. Okay? So the string along here is just, just 2 characters long. Now notice that we haven't put any nodes along here. We're just saying this is a path which we know eventually will be in the suffix tree. I don't know where the nodes will be put in there. But then I go over to, if you can run back to here, the next suffix that we want to put in the suffix tree represents the suffix that starts at position 4. And what we see here is that the longest common prefix between suffix 7 and suffix 4 has length 1. Okay, so those two prefixes agree for length 1, which tells me that what I should be doing here is modify this path by putting in a node which goes down to leaf 4. And what is the string depth along this shared path? We know what the string depth along the shared path is. It's 1. Okay? And so that the character along here is just character 7. We learn that from here. Therefore, this is just character 8. So when I put in this suffix for 4, I divided the path down to 7 in that way. And this is just a single character. So this is the suffix that starts at position 4. The first character must be up that way. And so therefore this substring is 5 through 8. Okay? So I now have learned a little bit more about the suffix tree. And notice, at least in this initial example, first part of it, what was the work involved in processing this leaf for 4? It was really just constant. I recognized that I had to divide this initial edge, which represented a path, and then I had to figure out how long was the substring here, how long is the substring here, and how long is the substring there. But those are just 3 operations, and it's just constant. We'll see that portion, the subdividing, is always constant, although finding where you want to subdivide isn't necessarily constant. Okay, then we go over to the suffix 1. And we know that where is the suffix 1? It should be hanging off of the path that leads to the suffix 4. And how far down do those two paths, for how long do those two paths share a path? It's for 2 characters. So we start at 4, and we know we have to go up to the point where that common path shares 2 characters. Well, this is, if we go up here, we know what this depth is. We have to do some arithmetic. But that tells us, since this is only a single, since this is what the length that is, we can see what that should be. And we realize we need to break here and put a 1. And then this 5/8 moves down. It's a 6/8. This is 5. That substring. And this is the suffix that begins at position 1, but we already have 2 characters there, so this one needs to be labeled with 3/8. Okay, 2 characters already taken. This is what's here is the remainder. All right, so in general, what you do is from every position, every successive position in the suffix array, you start at the leaf from its predecessor, and you look at how much is shared between those 2 paths. The path that goes down to 1, the leaf for 1, for example, which is already in the tree, and the leaf for 5, which you're trying to put into the tree, and you see what's the length of what they share. And based on that, you can walk up the path from this leaf to the root, and knowing how much they share and knowing what the lengths of this suffix is and what the lengths of the strings on each edge are that you're encountering, you can find the right place to spawn off a new path labeled with 5. So here, 5 and 1 share 0, so we know from 1 we walk all the way up to here, which is the 0 length sharing, put in a 5, and then this has to be 5 through 8, and so on. All right, so I hope it's clear that this algorithm builds a suffix tree. I hope it's clear that these 2 arrays, the suffix array and the LCP array, do specify the suffix tree. This is enough to specify completely what the suffix tree is. However, it may not be clear that the algorithm I just told you actually builds the suffix tree in linear time. Okay? And again, what's the general step in the algorithm? The general step is you've already put in all the suffixes from the beginning here to a particular point, and then you want to put in the next suffix. You know how long the path to that leaf is common with the path to the predecessor's leaf. And so you walk up from the leaf from the predecessor, knowing how long these suffixes are, knowing how many characters label each edge, you can figure out where this branching point should be in the tree, and then you put the branching point in a constant time, and you fix up the edge labels of all the three edges that are incident, or the three relevant edges that are incident to it. But why is this in linear time? Well, let me tell you, just sort of hand-waving in a way, what this is doing. This algorithm that I was just telling you for building the suffix tree here is, in a sense, just recreating the depth-first traversal of the suffix tree. That is, if you had the suffix tree already, which we did when we started out the lecture, we did a depth-first traversal to find the suffix array, a lexicographic depth-first traversal to find the suffix array, and then the LCP array tells you information about where two successive leaves in the depth-first traversal, what's the node, what's the lowest common ancestor between those two leaves, or where does the depth-first traversal go from going up to going down? So again, if we had the suffix tree and we wanted to build a suffix array for it, we could do a lexicographic depth-first traversal. In that lexicographic depth-first traversal, when you go from one leaf to the next leaf in the depth-first traversal, you have to go up a ways and then down a ways. How much you go up and how much you go down and how long the path is to the common point, if you know what this length is to the common point, and you know what the lengths of this suffix is, and the length of this suffix, which we do, then you can figure out exactly where that inflection point, or what I want to call it, the lowest common ancestor is. And the algorithm for going from the suffix array with the LCP to the suffix tree just follows that logic. It is just following the logic of how the suffix array was created backwards, in a sense, or maybe not back, just simulating it, but simulating it with the use of LCP. Now, I have a formal proof of that written down, but I think in a lecture, probably this kind of intuitive kind of explanation should be enough. And if you're not getting it, if you're not seeing that you can build the suffix tree in linear time from the suffix array and the LCP array, take that as a homework exercise and work it through. And I think everybody will see it in just a little bit of time. A key point that's you would have in a formal proof is that when you walk up from a leaf to a inflection point, a point where you're going from up to down, you may have to traverse through many nodes. And so the time to put in each successive leaf is not constant. The time to correct the labels that you need to correct is constant. But the time needed to find where you should spawn off the new path, that's not constant. Okay? However, what you have to argue to get linear time here more formally is that when you walk up from a leaf and you have to walk up through several nodes, you will never again walk up those nodes. Never again in the creation of the suffix tree walk up those specific nodes. The nodes you walked up to the point where you're going to put in a new node or recognize that that's an inflection point. Okay, and that comes from the definition of what the suffix tree is and what the suffix array is and so on. And you can do it very easily. So you either think intuitively that you're just building the suffix tree the way the depth-first traversal built the suffix array with the same logic, or you can do this more formally and notice that you never visit any node more than twice. Maybe once going down, and once when you create it, and then once when you walk back through it. Okay, I hope that's clear. I'm going to talk about other things that you can do with suffix arrays and LCP arrays later. Let's get to the main topic, which is how to build a LCP array in linear time. This had been open for many years, And I think shortly after it was found that you could build suffix arrays in linear time, maybe a year or two later, a paper came out that showed how to build the LCP array in linear time. Okay. Again, in describing this algorithm, it's very useful to think about the logic of the algorithm in terms of the suffix tree, even though the algorithm will not use an explicit suffix tree. But to see the logic of it, to see what's behind it, it's very useful to think about suffix trees. So I want to make a claim. Well, first of all, let me just write up something here. This is S. So we're always going to be thinking, we're really going to be thinking about three things or four things. The original string S, we're going to be thinking about the suffix array, we're going to be thinking about the suffix array, we're going to be thinking about LCP that we're trying to compute, and we're going to be thinking about the suffix tree. Okay, and sort of playing with all these at once helps explain what the algorithm is. All right, so if we have a particular entry in the suffix array, let's say it's k, that's not at position k, that's the value k sitting in the suffix array. And its predecessor, let's say, is j. So we see those two in the suffix array. Now, where are those two strings, where are those two suffixes in S? They could be anywhere, really. So I just draw this. Now, this is position k because we're talking about suffix k here. And let's just put j over here, although we don't know in general that j is to the left of k. It could be the other way. Okay, but this is suffix. This is the suffix beginning at position j, which is also the suffix beginning at position predecessor k, because j is equal to the predecessor of k. J equals predecessor of k. All right, and then in the suffix tree, what do we know? How do we represent j and k? So there's some path down the suffix tree, and j is the predecessor of k. So the depth-first traversal, the lexicographic depth-first traversal that builds the suffix array, is going to visit j, and then it's going to walk up here and visit k. And this. I'll label that node V. And I'll label this depth H. Okay? So the depth of this path, the number of strings, this is the root here. The number of characters along this path down to the place where the path to J and K diverge, that depth is equal to H, and so that's equal to the LCP of suffix K and suffix J. Okay, so we've got everything in place, all the pictures in place. We're going to be computing LCP values in order of we're going to be computing LCP values left to right in the LCP array. Okay? So we're going to be computing this value first, and then this value, and then this value, and so on. But when you compute this value, let's say LCP of k, okay, the LCP of k, then you need to go, just following the definitions, you need to find where k is in the suffix array. You have to find its predecessor, and then you have to find the longest common prefix between j and k, or similarly, you need to find this depth. So this should have been labeled h. This represents a common prefix between suffix sj and suffix sk. All right. All the players are in place. Unfortunately, I've used this board. We'll go back and forth to refer to it, but I want to draw up a claim and make a claim now. First, two claims, and then the algorithm will follow from those two claims. Now, actually, before I do that, let me write up what the completely naive algorithm. Naive algorithm for LCP, for the LCP values. And this is for k equal 2 up through n. Well, what's the most naive algorithm? What's the most direct way of finding the longest common prefix between two strings? Well, we need to know, of course, at every step, which two strings are we going to look at. So here we are at k. We look at the position of k in the suffix array. We find its predecessor, which is j. And then we can look into s itself explicitly and just do character comparisons, the two-fingered approach. The most classic algorithm we start with in any string algorithm is the two-fingered algorithm. One is on suffix k, one is suffix j, and then you compare the characters. Are they equal? If not, then we know that the LCP is 0. If they are equal, you move on by one position. You ask whether those two are equal. If they are, you move on by one position. If they're equal, you move on by one position, and so on until you finally find two characters that are not equal. And then you've found that the LCP value is h. So the direct, naive, two-fingered, let's compare explicitly, do the obvious thing algorithm takes order n squared time. So order n per k, which means order n squared total time. And the way I wanted to explain the faster algorithm, the order n algorithm, is just that it's a teeny trick that allows you to speed up the n squared to get down to order n. Okay, so to get to that teeny trick, we're going to use two claims. Claim 1. If, suppose we just finished computing LCP SK S predecessor of K. So we've just figured out what value we're going to put in at position K. LCP. This is terrible notation. Now I realize this is not good notation because the LCP array only has a single index. But when I defined LCP earlier, it was the length of the longest common prefix between these two suffixes. So LCP, where do we write this? We write this at position K of the LCP array. And I apologize for that ambiguity. I hope everybody understands that. Okay, so this value will be written at position K of the LCP array. So the LCP value of two particular suffixes will be written at this position of the LCP array. Of course, I should have, if I had done this properly from the beginning, this function of two strings would have a different name than the array that's recording that information. Okay, but suppose we've just computed that, and that LCP value is equal to h, and h is greater than 0. So they actually share, starting from position K, and starting from position predecessor of k, which over a minute ago I was writing as j, they actually share something, some amount, which is h, greater than 0. Okay? Then what LCP of sk plus 1 and s predecessor of k plus 1 is equal to h minus 1. Okay? Well, that's really rather trivial. The suffix that began at k, this is string s, the suffix that begins at k and the suffix that begins at predecessor of k, they shared exactly h common characters at the prefix. And then we had some character here, let's call it an x, and a character here, call it a y. Y might have been the end of string character, possibly. Well, actually, no. If you think about it, since k comes after j in the suffix array, this actually couldn't happen. All right, but at any rate, you get to a character x here and a character y that are not the same. X not equal to y. But if you were to start from, sorry, this I will eventually prove this, but not right now. Or I'll prove something like this, but not right now. This is the easy, supposed to be the easy one. Okay, so sorry. So the LCP of the suffix beginning at k plus 1 and the suffix beginning at j plus 1 is equal to h minus 1. So here we had the suffix beginning at k and the suffix beginning at j agreed for h positions, and then they deviated. So of course, if you look at position j plus 1 and position k plus 1, they agree for h minus 1 characters, and then they deviate. All right? So this is a triviality. The only thing that makes this hard is the notation. Okay, so if you can just keep your wits about you, which sometimes I have a problem doing, in reading the notation, this was a trivial comment. Okay, now another trivial comment is that, and it's again with this supposition that this value is equal to h, suffix k plus 1 is strictly lexicographically larger than suffix j plus 1. And again, that comes from the fact that that comes from the relationship of the suffix beginning at k and the suffix beginning at j. J was the predecessor of k in the suffix array. That means the suffix beginning at j is lexicographically smaller than the suffix beginning at k. All right, but they're identical for h characters. So when you look at the suffix that begins at j plus 1 and k plus 1, they're identical for h minus 1 characters. And then the next character over, we saw that the suffix beginning at j was lexicographically less than the suffix beginning at k. And so this means that x, that's the next character there, and y, the next character there, have that relationship. X has got to be smaller than y. And therefore, the suffix beginning at k plus 1 is strictly lexicographically less than the suffix beginning at j plus 1. Okay, this is claim 1, and this is easy. If it doesn't look easy at this point, stop. And when you're watching the video, stop the video and with your own hand do this. You'll see that this is a triviality. Okay. Next claim. The next claim is going to be similar to what I initially wrote down incorrectly over there. claim 2. And then from claim 2, we will really have everything. Okay, again, suppose h is greater than 0. Okay, then the LCP of suffix k plus 1 and suffix predecessor of k plus 1. Okay, and this is what we're interested in computing. After we've computed the LCP value for position k, we go on to compute the LCP value for position k plus 1. And this is exactly what we want to compute. It's the LCP of the longest common prefix of the suffix that begins at k plus 1 and the suffix that begins at the predecessor of k plus 1. Let's go back over here for a moment. Here we had learned something about the relationship, the longest common prefix between this suffix begins at k plus 1 and the suffix that begins at j plus 1. That's interesting, but it's not what we want to compute in the algorithm. What we want to compute in the algorithm at every iteration, every step, is the longest common prefix between an element, say k plus 1, and the suffix that begins at the predecessor position to k plus 1. So that's over here. So this is what the algorithm is actually computing. What we learned in claim 1 was something that's going to be useful. So here our claim is that this is greater than or equal to the LCP of sk plus 1 and sj plus 1, which we just established is greater than or equal to h minus 1. So this is what we just established in claim 1. And so the new thing in claim 2 is that what we're interested in computing at iteration k plus 1, what we're interested in computing is this, and this is greater than or equal to that. And since this is, this is equal, we know, is equal to h minus 1, so this value is greater than or equal to h minus 1. Okay, well, let's prove this. We're going to be able to prove this essentially by picture, by thinking again about the relationship of LCP values and suffix arrays to the suffix tree. Where do they all come from? Okay, so in the suffix tree, you have h minus 1. Here's j plus 1 to k plus 1. And here's a node v. So again, remember, we're in the special case where h is greater than 0. After computing LCP for at iteration k, h is something that's strictly greater than 0. And so what this said was that the length of the longest common prefix, or the longest common path, down to the suffix for j plus 1 and the leaf that represents the suffix for j plus 1 and the leaf that represents the suffix for k plus 1, that's h minus 1. So this is a picture that represents claim 1. Okay? And now, what are we trying to prove about this relationship? We're trying to put the suffix for the predecessor of k plus 1 into this picture. And by the way, let me just make a side comment. What is the index for the predecessor of k plus 1? Do we know? Anybody want to guess? J plus 1? Okay, I'm glad that somebody suggested j plus 1. That's not right. Okay? We don't know what the index, just with this notation, we don't know what the index is of the predecessor for k plus 1. So here's the suffix array. Here's where k is. Here's where j is. Okay? K plus 1 is somewhere. Don't know. And its predecessor is right there. What it is unknown from this notation. We would have to look it up in the suffix array. but it's not j plus 1. It's not j minus 1. We don't know. Okay, but back to this. Look at the picture. We know that this picture represents claim 1. And what we want to show is that the suffix for the predecessor of k plus 1 hangs off here, hangs off lower. It diverges from the path to k plus 1 someplace lower than this v. Okay? Well, let's suppose it doesn't. Let's suppose the path to the predecessor of k plus 1 hangs off the path to the suffix for k plus 1 somewhere above v. All right? So again, this is length or depth h minus 1. So the contradiction of this, the contrapositive of this, would be that the path down to the suffix for k plus 1 and the path down to the suffix for the predecessor of k plus 1, those two paths diverge up above the depth h minus 1. And again, what this says is that those two paths should diverge down here. All right, well, if that's the picture, now let's think about the lexicographic depth first traversal that builds the suffix array from this picture in the suffix tree. We know that predecessor k plus 1 comes before k plus 1 in the suffix array. So the lexicographic depth first traversal would come down here and go this way before it goes down that way. So it would come down, and then it would go that way, has to go that way, because the predecessor of k plus 1 comes before k plus 1 in the suffix array, which means this is lexicographically smaller than this. So the lexicographic smallest depth first traversal would come down here first. Then, after doing perhaps some other things, it eventually gets down to here. At this point, neither the suffix for j plus 1 or the suffix for k plus 1 has been visited by that lexicographic depth first traversal. Okay? That suffix, that traversal, let's say it visits k plus 1 before j plus 1. Well, that can't happen because what do we say? We said that the suffix k plus 1 is strictly lexicographically greater than the suffix for j plus 1. Okay? So if the depth first traversal went down and visited k plus 1 first before j plus 1, that would violate what we just were saying, that this is lexicographically larger than this. Okay? So the depth first traversal, once it's here, has to visit the leaf for j plus 1 before it visits the leaf for k plus 1. But that would then violate that this is the predecessor of k plus 1. The predecessor of k plus 1 is what you're supposed to visit immediately before. That leaf is the leaf you visit immediately before the leaf k plus 1. But now we're saying, no, you have to visit j plus 1 before k plus 1, and both of these are visited after predecessor k plus 1, which is, again, a contradiction to the definition of predecessor k plus 1, because this is supposed to be immediately before that. So that's the argument. I'm not going to write it down. There are written notes that are posted on the website associated with these lectures that write up exactly the argument I've given you. You can go back to the original paper, but the original paper doesn't do it graphically. It does it in a way, the algorithm develops the algorithm in a way I find very confusing. So, but anyway, let's fix the picture to show exactly what is the story here. What we've just proven is that predecessor k plus 1 has to hang off of here, which means we've just proven claim 2. Okay? So claim 2 is proven by the argument that I just gave you on the picture. Now let's fix up the naive algorithm, the two-fingered algorithm. Let's fix that up so that it runs in linear time using claim 2. How do we do that? So we're trying to fill in LCP. We've just filled in K. We've filled in the K value, and that's H greater than 0. Well, here's the suffix array. Sorry, this is, yeah, okay, suffix array, and here's S. Okay? So we've just found the predecessor, we just found the LCP value for K, and it happens to be H, where H is greater than 0. Then we move on to K plus 1, and first thing we do, you look into the suffix array to find K plus 1. Well, of course, you have to have the right data structure so that you can find the position of K plus 1 in constant time. That's all minor data structure issues. Of course, you don't want to scan the suffix array to find where K plus 1 is. You have some inverted array that you built when you build the suffix array. Totally trivial stuff. So you know where K plus 1 is, and you find here the predecessor of K plus 1. Okay? So then here's the predecessor of K plus 1. Here's K plus 1. Again, we don't know that K plus 1 is to the right of the predecessor, but it's just in that drawing. And if you use the two-finger approach at this point, you would just compare these characters one after another until you found a mismatch. But this theorem, claim 2, go back to claim 2 for a moment. Claim 2 says that the two strings, the two substrings, the one that begins at position K plus 1, and the one that begins at the predecessor of K plus 1, those two will agree for at least H minus 1 characters. So in the two-fingered approach, you don't have to start at the beginning of the suffix K plus 1 and the suffix for predecessor K plus 1. You can move out H minus 1 characters. Skip over H minus 1 characters. Okay? So you would skip over H minus 1 characters here, skip over H minus 1 characters, and start here. You'd start your explicit comparisons from this position forward until you, as long as you're getting matches, and then you finally find a mismatch. And that tells you, of course, what the LCP value is between K plus 1 and the predecessor of K plus 1, and you would write that value right there. Okay, everybody get it? Claim 2 just tells you an immediate speed up of the naive algorithm, the two-fingered explicit comparison algorithm. It says if H was bigger than 0, then we can skip forward by H minus 1 characters at the next iteration and never do those explicit comparisons. And that's it. That's the whole algorithm. The algorithm is do the two-fingered algorithm, but whenever H is bigger than 0, skip forward H minus 1 characters at the next iteration. If H is equal to 0, you can't skip at all. You just have to explicitly do the two-fingered comparison. So the algorithm is compute LCP in order of K equals 2 through N. Use naive when needed. But if LCP at K is equal to H greater than 0, then skip H minus 1 characters when computing LCP K plus 1. Now this LCP here, we're talking about the array value. Now the correctness of this, it comes from claim 2. We've proven the correctness of this. There's no issue now whether this algorithm correctly computes LCP values. The only issue now is time analysis. This claim 2 that skips certain comparisons is clearly a useful thing. It certainly speeds you up, it never slows you down. There's really virtually no overhead in it compared to the naive algorithm. You just have to note when h is bigger than 0. So it's clearly a good idea, okay? But does it give you the linear time algorithm? And to see that it gives you a linear time algorithm, we're going to use an argument that's sometimes called the bouncing ball argument, or at any rate, we're just going to be paying attention to what are the successive LCP values that are being computed as you go through the algorithm. Okay? So and here, so claim the improved algorithm, the speed up algorithm or sped up algorithm runs in order n time. And the proof of that, as I said, is just at the start and end of each iteration, that is, for each successive value k that we're using, that we're looking at, let's just take note actually, let me give this an index of iteration, let's say k plus 1. Take note of what is known about the LCP of k plus 1 value. Okay? So, compared to LCP of k, the LCP value you just put in at position k of the LCP array. All right? So at the start, and we're also going to look at the end, but okay, at the start, LCP of k plus 1, either it starts off, I mean, what we know about the LCP of k plus 1, the only thing we know about it is that it might be equal to 0. And in that case, that's the case when LCP of k was equal to 0 or 1. In the case when LCP of k is 0 or 1, at the beginning when we're computing LCP of k plus 1, the only thing we know is that it might be 0. Okay? So it's greater than or equal. So if you're listening to this, if you're watching this without sound, this won't necessarily make sense because this notation isn't terribly sensible. So let me say this again. At the start of iteration k plus 1, what we know at that moment is that the LCP of k plus 1 is greater than or equal to 0, and we know that when it happened to be the case that the LCP of k was equal to 0 or 1. Okay? But the other case is that LCP of k plus 1 is greater than or equal to h minus 1. I guess I should have said, this should have just said when. And this is when LCP of k is equal to h. Okay? This is from claim 2. So at the start of every iteration, what we know about the LCP of k plus 1 is that it is at most one less, or at least one less. It might be, the LCP of k plus 1 might be one less than the LCP of k. So if we're looking at what do we know about LCP at any given moment in the algorithm, at the beginning of an iteration, we go back one value from where the LCP was, at most one value from where it was before. We finished iteration k, and we found that the LCP was h, where it was 0 and 1. And then if it's 0 and 1, what we start out with at iteration k plus 1 is that it's 0. At that point, it'll get bigger in iteration k plus 1. It could get. Similarly, if when we end iteration k, the LCP is h, which is bigger than 0, then we know at the beginning of iteration k plus 1 that the LCP of k plus 1 is at least h minus 1. So it just goes back by 1. So if we're looking at the successive LCP values at the beginning of any iteration, what we know about it is that it goes back at most by 1 compared to where you ended up in the previous iteration. Okay? And then how does it increase? So that's the decrease. We've just looked at how LCP values decrease over the running of the algorithm. The instantaneous LCP values decrease. During iteration k plus 1, the LCP value increases. So you call it the instantaneous LCP value, or the bouncing ball. It increases by the number of character matches done during the explicit character comparisons. The two-fingered part of the algorithm. And so over the life of the algorithm, over the entire running of the algorithm, so the instantaneous, however that's spelled, instantaneous LCP can decrease by at most n. In each iteration, it either decreases by 1, or if we're in the 0 case, it doesn't decrease at all. We have n iterations, or actually n minus 1 iterations. We have a decrease of value 1 at the start of each iteration at most. And so the total decreasing is n. Okay? But LCP value is always less than or equal to n. Again, because the string length is n. Again, this can be n minus 1. So if you can decrease by at most 1, and you can never go bigger than n, and the amount that you increase in each iteration is exactly equal to the number of matches, this implies the number of matches is less than or equal to 2n. Okay? The bouncing ball goes forward when we have a match and goes backwards by 1 at most at the beginning of any iteration, and its total amount that it travels backwards is at most n. It can never go past n, and therefore, the number of the amount that it goes forwards is exactly equal to the number of matches. So the total number of matches is less than or equal to 2n. Now, in each iteration, if we end up doing, when we do explicit comparisons in the naive algorithm part of that iteration, we stop as soon as there's a mismatch. So the number of mismatches is bounded by n. That's trivial. Number of mismatch is less than or equal to n. Okay? Well, again, n minus 1, because we only have n minus 1 iterations. So the total number of comparisons is less than or equal to 3n. And the algorithm, the time that the algorithm takes, is certainly bounded by, is proportional to the number of comparisons that are done. All the other operations in the algorithm, looking at h to see if it's bigger than 0 or whatever, and subtracting by 1 and moving forward. That's all constant time. So, so this implies that the time for the algorithm is order n. I hope you can see that in the video. And that's it. That's the time bound. That is the proof of the time bound. So the algorithm is really a very simple modification of the most trivial, immediate, naive algorithm using claim 2. And claim 2 is proven really by a picture and thinking of the definitions. And then showing that the time bound is linear is this really classic style of algorithm I call bouncing ball, but you have some quantity. In this case, I guess I'm calling it the instantaneous LCP value, and you're looking at how that changes as the algorithm runs, and you're noting that it can total decrease, that it can happen as it bounded by n. The total increase is bounded by 2n, is bounded by n. No, 2n, sorry, is 2n. The number of matches is 2n. So we have 3n here, and then we have another n for the mismatches, and then we're order n. Okay, I've got 3 minutes left. I really want to show you, there's lots of things you can do with LCB and suffix array. Let's just do one very quickly. I may have to leave the justification of this as a homework exercise. So, longest common substring of two strings. Okay, so we have a string A and we have a string B, and if you start at some position, let's say I, and some position J in the second string, these may agree for some length, ABWX, ABWX, and Z and P. So they agree for a length of 4. And the question is, given A and B, but you're not given the individual positions, find the longest common substring. Find a substring that exists in A and a substring that exists in B, somewhere in A, somewhere in B, not necessarily at the same position, not at known positions, that are identical, and what's the longest one? The naive algorithm for this is like n cubed. You have n squared, these are both length n. You have n squared positions, pairs of positions. If you look naively, the time you would allocate for that is order n, so that would be n cubed naively. But in fact, you can do this in order n time. It's a classic thing with a suffix tree. And with a suffix array, actually what you do is you look at the LCP values and you note where you have, you look at the, you want to find two successive positions where one comes from A and one comes from B. So you build a suffix array for A combined with B, with some kind of delimiter in between. And you want to find a position in the suffix array where you have A, either A followed by B or B followed by A. And then you look at the LCP value for all those positions where you have an A followed by a B or a B followed by an A. You look at the LCP value and you find the max of those. And so clearly that can be done in linear time. You're just scanning through the suffix array to find the candidates. You're looking down at the LCP values, find the largest of those particular LCP values, and that tells you what the two substrings are, one from A and one from B, that are longest common substring. Well, I don't have time to prove this, but it does show you another of many applications, many algorithms that you can where you can use LCP and suffix array to solve a string problem in linear time. That had been done earlier in suffix trees. Let me just say one thing about suffix trees. There are problems, string problems, that are solved in exponential time without suffix trees. They're solved in linear time with suffix trees. A huge, huge improvement. And those problems also can be solved with suffix arrays. They're much more complicated than this one. But that's it. We're running out of time. Thank you very much.